Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So let's continue, and we had talked about various principles, and we talk about different means how to achieve higher precision and then accuracy. So we also try to understand with different examples. We have discussed some of them, but we take some examples and some case studies, and we try to understand how these principles are used to achieve the level of precision what is required for those kind of applications. So today we'll concentrate on one of the setup I designed for my PhD thesis, and that was for robotic surgery. And if we talk about minimally invasive surgery, it's getting incorporated with robotics. And if you are aware of, like Da Vinci robots, they are the state of the art systems, and world over in various hospitals they are used to carry out operations, surgical operations. And even in India, many of the hospitals they already have. And what is the way forward? What kind of precision is required to develop those kind of systems? Of course, the reliability, the safety is of the utmost concern, and the precision is always with respect to the safety requirements. So, the topic today is the telemanipulation of flexible instruments for robotic minimally invasive surgery. So, if you look at it, and we look at the current trends in surgery, what we realize that the surgery now is from the open surgery. So, if we talk in terms of invasiveness, if we look at open surgery, uh, there is a lot of damage to the healthy tissues, and it's mainly because there is no access. So, the surgeon has to operate and work at the site, which is many times inside the body. So, create that access, the surgeon has to create that opening and work at the site on the organ or whichever part is affected. So, to address that open surgery, laparoscopic surgery has come up, and now it has become keyhole surgery. So, you just insert 12 to 16 kind of instrument, rigid instruments inside the body, and then you try to operate from the outside. So, of course, in terms of invasiveness, it has reduced considerably, but it has imposed a lot of challenge and constraint to the surgeon. The dexterous space is now compromised. You have to work through instrument, and that was a challenge. So, but definitely the invasiveness in surgery is getting reduced. So, this is what it means. Minimally invasive surgery, MIS, is becoming less invasive. On the other hand, if you look at the flexible instruments, what used to happen earlier, the flexible endoscopy usually is inserted through openings. It can be through natural openings also, and it can go inside the body. And initially, it was mainly for diagnosis. You just try to see, observe, and try to see if there is anything wrong. But slowly what has happened, because if you have detected something, you may want to address then and there itself. So you have started introducing instruments. So for instance, if you see this kind of instruments coming out of the endoscope, so you try to address, so you try to add some invasiveness and try to address that. So the endoscopy is becoming more invasive. So what you see is there is a convergence. So from the surgery point of view, the invasiveness you want to reduce. For diagnostic purposes, you are using the flexible instruments or endoscopy, and now slowly you wanted to insert uh, instruments through different channels. You have started making provisions for that, and then so what we see that there is a convergence, and then of course the both can meet and can solve a lot of problems. So that was the trend. And in robotic surgery, if we talk about robotic minimally invasive surgery, the biggest advantage is the whatever is the limitation imposed by the insertion point on the instruments and thereby on the surgeon, that can be addressed if we use robotic means, or if we use the concept of robotics and integrate with those instruments, we can overcome a lot of challenges. And that's why it was envisaged that the telemanipulation or the master and slave configuration, master slave based telemanipulation is the way forward, and that is the state of the art today. So this is uh, how it looks like with the Da Vinci robots from Intuitive Surgical. So there are many such systems commercially available, and world over the researchers are working on different kind of setups. But yes, because of the regulation and because of the safety requirements, not many are still or not available commercially. But Da Vinci is definitely there, and different versions are available. However, they are very expensive, and it's very difficult for common man to afford surgeries using these kind of systems. So yes, the commercial aspect is there, the uh, cost is involved. So that is one aspect. But technology wise, if we try to look into these systems, what we realize that it's a very good, and they have addressed many challenges. So in terms of usage, if we see, and what it means when we say master slave. So yes, it's a medical related, and of course the expert is the surgeon, the medical professional, who knows better what has to be done, and what kind of treatment is required, what kind of interventions are required. So that's why the master is the surgeon, and it controls the instrument and operate on the patient through the instruments through the master console. So it's one unit, it's a separate unit, but via that the surgeon control each and everything. So what it provides is, it provides all the freedom, the dexterity what a surgeon needs. So the manipulator, the kind of human machine interface provided there is very intuitive, and the surgeon is very happy to work with that, because he can get all kind of feedback, and as if he is working on the site on the particular organ or doing the particular interventions with his hands. So, it is a very immersive. So, all those capabilities are there, are inbuilt in the master console, but is a separate from the patient. How it communicates with the patient is through the wire, or we can say wireless also. So, now whatever command and whatever is the information, whatever is the intended operation or procedures required is getting translated and getting transferred to the slave side, which is again a robotic manipulator. So, this is the slave side. So, master manipulator, set of manipulators, and this is the patient, and the instruments are inserted inside the body, and this is the master console, and you can see the surgeons can now sit down. So, now 2-3 surgeons can also operate and can supervise. So, what it provides is the slave side is optimized for the intervention, kind of intervention required. So, it's a plus for both for the surgeon, and since for the patient is through the keyhole, so the damage to the tissues is reduced, and the person can return to healthy life, to the normal life very quickly. The stays in the hospital can be reduced to 2-3 days in many cases. So, which is very good, and that's what surgical robotics provides you. So, and but at the same time, it doesn't compromise with the quality of surgery. In fact, it has improved the quality of surgery, and quality of post-operative uh, complications are reduced. So, the person can come back quickly and can lead a healthy life. What it also provides, what you see here is, this is the master side and this is the slave side. But these two operations, the surgeon can see, and what the surgeon sees is this, but just below that he's working with he or she is working with the master manipulator, manipulating things. So as if he is working with those knives, those suturing devices there itself, then and there itself. So it provides a lot of advantages, and that's why world over, more than, I think more than 80% of the surgeries are done robotically. Only in the extreme cases you go for the open surgery. On the other hand, what you see that all those even in Da Vinci and even in the latest one, the instrument, kind of instrument you have is they are rigid instruments. They are articulated. The tip can be articulated, but they are rigid. So they have certain disadvantages and what I can say some limitations. On the other hand, the flexible instrument which can go with the endoscopic platforms or different kind of endoscopes, they it can flex very easily, bend very easily, and it can navigate inside the body. So they are very flexible, and definitely it can go beyond diagnostic tools. And the idea was to use this flexible instrument instead of rigid instruments in Da Vinci kind of setup. So these are some of the examples how these flexible instruments are used in a surgical scenario. So although it's a limited, but yes, they are still used to carry out the different kind of procedures inside the body. Yes, the challenge is the flexibility is advantage, but at the same time it also gives you a lot of challenges and limits the its a use in those kind of setup. So the idea was to use this kind of flexible instruments in a master slave configuration, and that's why we have telemanipulation system with the intuitive control for transluminal endoscopic surgery, and in short it was called teleflex. And of course you have the division, you have master and slave. Master side, usually you don't see much problem because yes, these manipulators can be designed and there are a lot of solutions, mechanisms there to help you. So that is more or less like these days you can use a different kind of HMI. You can use manipulators which can be suited or can mimic the open surgery for the intervention what is required. On the other side, on the slave side, if you see, and if you want to use flexible instruments, there are limitations, and that's something we wanted to address at that time, and it's still a challenge. Many people are still working in this area and try to improve the system so that we can get advantage of flexible instruments, and whether we can integrate these flexible instruments in the robotic system and can make full use of that. So ultimately the beneficiary is the patient, but at the same time you don't want to limit the master or the surgeon. So when we look at this kind of scenario, what we realize that the control of flexible instruments or endoscopes is challenging, and the motion and the force delivery at the instrument tip is going to be again very challenging. So what is the fidelity? Because in all these cases what we see that the actuation is lying outside the body and the instrument is way inside the body, and yes, it's changing the shape, the geometry of the channel, the platform is changing. It has a lot of friction because of the limited stiffness. Also, we have a lot of issues. We have seen that if the friction and the stiffness, if friction is there and the stiffness is also low, then there can be a big difference mm, in the positioning, and what we also call is virtual play, what we have seen in those cases. So all those problems will creep in, and then we have to address that. So this was very challenging and we try to address that. So some target intervention we propose at that time. So very simple cases where a submucosal removal you have to do. So inside the our intestine, if it's um, the tissue is cancerous or malignant, then you may try to lift it and cut it and remove that section. So even for doing that kind of surgeries and those kind of procedure, it's not easy because the the endoscope is flexible. So there are different strategies and different kind of endoscopes where the that section can be rigidized, and then you have the access for the instrument, so instrument can come out. So you use some way to triangulate and operate, but it's still the dexterous space is very small and very difficult to work with. So we targeted the endoluminal procedures and try to do operate or check the efficacy of the system on these kind of interventions. And some interventions we can do, we can just do the biopsies or polypectomy, take the samples out and try to see. So and reduce the time. So now if we look at flexible endoscopic surgery, the constraints what we have is the instrument tip is remotely controlled, the friction between the instrument and the guide tube, shape of the tube is changing all the time, the instrument has a limited stiffness, and of course it has a clearance also so that it can move easily. So the challenge what we have is how to ensure motion and force fidelity, and how to get a predictable behavior. So this is just to showcase like how it's done. So endoscope can be inserted and can operate. So there are various setups. So Boston Scientific is a manual from outside. You can operate with these handles and can operate on this tape. And this is conventional normal cornoscope from Olympus. So there are various setups now these days. Yes, so we wanted to study the dynamic behavior of a flexible surgical instrument inside the endoscope, and we carried out the modeling and simulation to understand more about the interaction, how these instruments behave under those circumstances, develop the experimental setup to know exactly how the different parameters are related and what kind of behavior can be expected. And of course, later we have to do the validation, testing, characterization. And when we look at the modeling, so this is the kind of typical setup we have: the endoscopes and flexible instrument. Two, again, very flexible, but at the same time you also need to address how they interact. So the instrument, the access channel provided inside the endoscope, and the interaction, the contact. So all these things we have to define so that we can get a better model and we can simulate different phenomena. So for the flexible instrument, again, this is a finite element approach, and uh, what we develop is the model for the instrument, and for the tube, for the access channel, we define a tube. And what we wanted to have is not just the translation, but the rotary motion, whether we can give it. And then if we do that, what happens? And the tube is defined by the Bezier curve. And the Bezier curve, we know that it needs a minimum number of control points, and we can design different kind of curvature. So we use the Bezier curve to define the shape, and then we assume that is a uniform circular cross section. Of course, since we can assume it's rigid, so to start with we assumed it's rigid, but it can be flexible also. So that is something, those are the modeling challenges. And okay, contact model we defined, and different region we defined and calculated different triads at the point of interaction, define the stiffness, damping, and friction. And so these are something, maybe if you are interested you can refer to the literature, but no need to understand everything. I think what is important is how it's used. So at the point of contact, I think this is what I discussed earlier also. At the point of contact, and when it's moving, what happens? What kind of forces are there? So there will be normal reaction force, and accordingly there will be friction force. So what you see here is the tangent plane and the normal force. You can have the normal force there, and tangent plane is defined. So if you have the rotation also, you can also see what is the effective movement. So we can get again the direction based on the slip velocity, and we can also do some simulation and suppose what happens if we insert. So what kind of forces will be there during the insertion at different nodes? So we can see that okay, the arrows, the magnitude, it can show that whatever the forces as is moving forward, and the magnitude you can see here, the force magnitude. It's important to know because large force on the organ, so it's although it's inside, but if it's outside and interacting with the tissue, the forces can be way higher, and it can damage the tissue, and even we can have a perforation, which is highly undesirable. So that was the modeling part, and yes, one can use a different kind of tools. A lot of finite element methods or different tools are there these days, so one can use those tools. So now when it comes to characterization and to the measurement, like what to do, so of course we want to have our own experimental setup so that we can do whatever you like. So we want to manipulate the instrument from the base, from the proximal end, different kind of motion we want to give. We also want to see what is happening at the tip. So want to measure precisely what's happening at the instrument tip, how much is moving forward or backward rotation, if there is any whip like motion, if it's suddenly moving. So that is something not desired. So we also want to see that. At the same time, what we also want to have is force of interaction between the instrument and the tube. So when it's interacting, when we are manipulating the instrument, what are the forces? What can we measure that? So we also want to do that. So that was the basis for the setup. And then, so based on that, we started working, and then what we realized that we try to divide and make it modular. So for the instrument and to actuate it, we need the actuation module. For force measurement, we need a force sensing module, and for the tip measurement, we call it tip motion measurement module. So this is how it will look like. So actuation block is there, actuation module. So the different kind of actuator sensors there, and from the base we can manipulate the instrument. Output block we have here, so can measure it, and preferably non-contact type. The reaction platform here, there are various reaction pads, so some concept, so the tube can be fixed, and if there is any force, can we measure it precisely. So that was the idea, and that's how we wanted to do. So looking at the actuation module again, so we wanted to have translation and rotation at the same time and want to combine and also see. So these are some numbers, yes, the designer specification we should have to proceed. So from the literature, from the surveys, after meeting with the surgeon, we know what is the kind of numbers they are looking at. And very simple concept for the actuation module, and what we have here is very simple design. So linear guide you see here, so it can slide, and on this side you can see the ball screw on this side, motor is there. But what happens, yeah, means if it's just a kind of mechatronic application or any, not looking for precision, we can just, assuming they are aligned and some it can easily take, so we can simply attach them. But if we look at from precision point of view, what we wanted to have is, we wanted to just transfer the translation of the nut, ball screw nut. So wanted to have one constraint, the linear constraint in that direction. At the same time, we don't want to clamp it through bolts. So what we wanted to have is, wanted to restrict the torsional motion or the torque, so that that's how the ball screw will work. So we come up with the flexure coupling. So, and we have two, one is bellow flexure and one is folded sheet flexure. So folded sheet flexure, what we know that it provides constraint along this line, along the fold line, and the bellow will provide the rotational constraint. So if it's a rotation is constrained, so the nut will not rotate, but since the motor is rotating, So because of the helix angle, the ball screw, the pitching, it will translate. So what we will get is only the translation. So any kind of angularity, offset, whatever we have, that can be absorbed by this flexure coupling. So we come up with this and we design, and this is what we have. This is how it will look like. The next was the force sensing module, and this is something I think really interesting, and we want to know how it can be designed. So we wanted to know the forces in all the directions, so 6 load cells. One of the option could be to simply use 6 top load cell, but if you want to know exactly what's happening, it's also good to design our own. So what we try to do is we try to use single DOF load cell embedded, and then we use the 3-to-1 configuration what we discussed earlier. So this will again we cover and try to understand how it's used, and then we use the wire flexures and connected it, and then we developed the entire setup and we used it. So today I think we are going to stop here, and I'll continue in the next lecture from here. Thank you.